So we're going to talk about concavity, a very important concept in calculus, and this ties into something else that we're going to deal with about the second derivative test. So just to review, the first derivative test is kind of a general term. So we have the first derivative test for extrema, which is kind of a better name for it. A first derivative test for extrema. And extrema are mins and maxes on a graph. And we have a first derivative test. We do that by using a sine test, or as I've coined, a secant test. A sine test on f prime to find intervals where f is increasing or decreasing. So if I'm going to chart this out, this is probably one of the most important charts you can ever do in calculus, where we have f, the function, that when f is increasing, what is happening with f prime? Well, f prime is positive. And when f is decreasing, f prime is negative. So I'm going to put a little chart here and start to build this out. But now we're actually going to expand this chart, and we're going to look at the second derivative. And so the second derivative, first what I'm going to say is that when the first derivative is increasing, the second derivative is positive, and when the first derivative is decreasing, the second derivative is negative. That should make sense. Really, all I did was I took these two categories here and just slid them down a spot, which the same relationship would hold true. But what it means for the first derivative to be increasing and decreasing, let me kind of change the color of this to sort of match the what we're doing. If I now look at the original f function, when f prime is increasing, that means the slope of the tangent line of the graph is getting larger. So the shape tends to look like that. Because if I travel from left to right, here I have very negative slopes, and if I move to the right, they can become very positive. So that means that the slopes themselves are increasing. And the opposite is true. Decreasing for f prime makes that. We have some names for this. This is called concave up, and this is called concave down. So concave up is when f prime is increasing and f double prime is positive. To kind of look at a graph where this is happening, let's just look at a basic sine graph. So I'm going to kind of draw a sine graph. Let me do another loop here. And we have a couple of ways that I can look at this. I'm going to put it sort of these points down. These little points here, we're going to call points of inflection, because those are points where the graph changes from concave up, which looks like this, so I can kind of characterize those here. Those are all concave up, to concave down, which looks like this, and those are these places here. Additionally, I can kind of characterize where is the graph itself increasing, where is the graph itself decreasing. So increasing actually goes from min to max. So this is a region where the graph is increasing. And you can see that there, and there's another one here. Then the opposite of that is where it's decreasing. So this really, really means you have to have a lot of ideas and keep them straight here. So let me go back, and we're going to look at this not from a perspective of concavity. We're going to look at this from a perspective of increasing, decreasing only. So I'm going to keep this graph here, and what I'm going to do is look at where f prime of x is greater than 0, and we're going to do a yellow highlight on that. And then we're going to do where f prime of x is less than 0. I'm going to do a blue highlight on that. So again, f prime of x greater than 0 means the graph is increasing. Oops. So increasing is here to here, here to here, here to here. And decreasing is right down here and right down there. There we go. And then any place where f prime of x is equal to 0 are these points here that we call local extrema. That's a first derivative in a nutshell about where it's positive and negative. So looking at this same graph now from the perspective of a second derivative, which is what I did earlier, what I get is now I would be looking where f double prime is less than 0. F double prime is less than 0 anytime the graph is concave down, and that looks like this. So that is going to be, let's do that in blue. Oh no, I already selected the yellow. Let's do it in yellow. That's going to be this, and this, and this, and then f double prime greater than 0 is where the graph is concave up, which looks like that. So that in blue is going to be this region, and this region, and this region. And then, as we said before, anytime f double prime is equal to 0, that's these points that transition from concave up to concave down, and those are called points of inflection. So let's take a look at some of what this enables us to kind of look at. Let's start with a graph that you all know, y equals x squared. Y equals x squared is a parabola. Y prime is equal to 2x, and y double prime is equal to 2. Well, I know that 2 is greater than 0, which means that y is concave up on negative infinity to infinity. And if I graph just a basic sketch of this, I see that. The graph of y equals x squared looks like this. So I'm going to go all the way back up to the heading, and we're going to call this concavity. And the second derivative test for concavity. So going all the way back down, let's do another one. Nope, I don't. Let's look at y equals x cubed plus 1. Y prime would then be 3x squared. Y double prime would then be 6x. So if I do a sign test on the second derivative, well, I know that 6x is equal to 0 when x is equal to 0. And if I look at the second derivative and do a sign test where I put 0 in as a critical value for the second derivative, let's look and compare it on the second derivative. And I want to be clear, we are doing a sign test on the second derivative. What I end up with is positive to the right of 0, negative to the left of 0. This basically means that f double prime is greater than 0 when x is greater than 0, and f double prime is less than 0 when x is less than 0. So its concavity changes at x equals 0. And if I graph this x cubed plus 1, just to kind of recall what that looks like, it looks like this. And I can see that at x equals 0, I'm going from one concavity to another. That means that x equals 0 is a point of inflection. Another one I can give you, g of x is equal to negative x cubed plus 3x squared minus 2. And I'm going to do that, well, I don't like that form of g of x, so since it has a negative leading coefficient, I'm going to factor that out and make it a negative x, or an x cubed minus 3x squared plus 2. I want to try to graph this, and I want to graph this and find out as much as I can about how to graph this and how this looks. So first what I'm going to do is on the first, or the original function, I'm going to find its zeros. Now, this is tricky because this isn't easily factorable. To do that, what I want to do is I want to try to divide this by things I think might be zeros. And looking at that 2 there, I know that some of my zeros might be 2 or 1, or negative 2 or negative 1. So I'm going to divide this by x minus 1 to see if it divides, but I'm not going to do division like this. And if you want to see me to learn about synthetic division, it's wonderful. I'm going to divide by 1, which is the root of x minus 1. I'm going to put down the coefficients, and I'm going to fly through this because if you've never done this and you want to learn how, come and find me again. So what I do is I multiply, and then I add, and then I multiply, then I add, then I multiply, and then I add, and I got a remainder 0. The remaining terms here correlate to an x squared minus 2x minus 2, and this correlates to an x minus 1, and we still have that negative that was out in front, and believe it or not, I just factored that. I just pulled out an x minus 1, and that happened to have been a perfect factor of that. So that means that I have zeros at x equals 1, and x is equal to, let's do the quadratic formula, 2 plus or minus square root of 4 minus 4 times 1 times negative 2 all over 2. So I get x is equal to 2 plus or minus the square root of 12 over 2, or x is equal to 1 plus or minus, that would be 2 root 3, so root 3. And that's about, let's see, root 3 is about 1.7, so that's about 2.7, or negative 0.7. So moving on to other things that we need to have. G prime, let's look at G prime of x, is negative x squared plus 6x. And if I pull out a negative 3x, I get x minus 2. This means that my critical values on the first derivative are 0 and 2. So if I do a sign test on the first derivative with critical values of 0 and 2, I'm going to get negative plus, or minus plus minus. That means that g is decreasing on negative infinity to 0 and 2 to infinity. And g is decreasing on that since g prime of x is less than 0. You kind of have to give that reason as the reason that it's decreasing. And g is increasing on 0 to 2 since g prime of x is greater than 0. The sign test is for u, but that's not enough to put in a verbal description of why this is as such. So now let's look at an analysis of g double prime. You're going to get negative 6x plus 6, and if I factor the negative 6 out, I get an x minus 1. So I have a critical value on the second derivative of 1, and if I do a sign test on that, I'm going to get a negative and then a positive. So this is saying that g is concave up on negative infinity to 1, and g is concave down. Oh, I forgot my reason. G is concave up on negative infinity to 1 since g double prime of x is greater than 0. And then I'm going to say g is concave down on 1 to infinity since g double prime of x is less than 0. So now I'm going to try to make an actual sketch of this, given the information that we have. And hang on, let me minimize this. Okay, so I mean by sketch, like this is just going to be a basic sketch. So we have zeros at x equals 1, 2.7, and negative 0.7. So we're going to put one here, one here, one here. So negative 0.7, 1, and 2.7. And I know that at 0 and 2, the graph is, those are changes from decreasing to increasing. So if I get my graph going from decreasing here to 0, and then increasing, so 0 to 2, it's increasing, and then from here down below, it's decreasing. And then finally, I have a change in concavity occurring at x equals 1. So right here, that's a change in concavity, and that matches. Like right here, I can see that I have a concave up portion, and right here I can see that I have a concave down portion. So this is just a basic sketch using the zeros the critical values kind of here at x equals 0 and x equals 2. We're just going to kind of call that x equals 2. And then, again, this was about 2.7 for the 0. But this is a pretty solid sketch of the graph. And that's sort of why we're doing this, is because really we can get a complete picture of these graphs by using the derivatives. So let's move on and talk about a second derivative test. As a test for concavity. So I'm going to list out steps here. First of all, number 1, find f double prime. Number 2, let f double prime equal 0 or f double prime not exist. And then finally, do a Sine test on f double prime. So as another example, let's see, this would be example, I should number these. We'll call that 2. Nope, that should be 1. This should be 2. That's 3. And so this is now example 4. Let's do f of x is equal to 2x cubed minus 3x squared minus 12x plus 5. Well, we need to find f prime of x. Now, what I'm going to do, I'm going to do a little bit, go above and beyond. Let's find f prime, and let's just figure out some things about f prime. So here's f prime, and before I go and find the second derivative, I'm going to actually factor this. So I get 6, and I'm going to have an x minus 2 and an x plus 1. And I know that the critical values on f prime are -1 and 2. So then next, that's just kind of a little aside. I'm going to put that in parentheses. Let's find f double prime, which is 12x minus 6. And if I factor that, I get 6 times 2x minus 1. And then I know that I have critical values at x is equal to 1/2. So if I do a Sine test with 1/2, now it goes positive, negative. And I know that the graph is concave up on 1/2 to infinity, since f double prime of x is greater than 0, and x is concave. It's concave down on negative infinity to 1/2, since f double prime of x is less than 0. Now, the reason, this is kind of what I asked for, but I want to sort of go a little aside here. The reason I found the critical values at -1 and 2 is that I know that there are relative extrema at x is equal to -1 and x is equal to 2. If I want to know if those are mins or maxes, I could look at a Sine test on the first derivative. But I can also plug x equals -1 and x equals 2 into the second derivative. So let's figure out what happens. If I do f double prime of -1, what I get is 6 times 2 times -1 minus 1, which is the same as 6 times -3. Which I don't really care what that is. That is less than 0. That means that the graph is concave down at x is equal to -1. So if I know the graph is concave down at x equals -1, which looks like this, and I know that x equals -1 is either a min or a max, therefore I know that there is a max at x is equal to -1. If I do the same thing on the other one, f double prime of 2 is equal to 6 times 2 times 2 minus 1. What I get is 6 times 3, which is definitely greater than 0, which means that the graph is concave up at x is equal to 2. Concave up looks like this, and therefore there is a minimum at x equals 2. This is something that we're going to be repeating a lot in the coming days. This right here is called a second derivative test for extrema. It can be used as a quicker way from the first derivative test, but the first derivative test for extrema is a better test, and we'll be discussing that more in the coming days.